let's start. And I'm happy to announce our first speaker today, who is Baohua Fu from AMSS and Morning Site Center in Beijing. And he will tell about deformation rigidity of Fano manifolds.
Okay, thank you. Thank you for the invitation, and also thank you for coming to my talk. So I'm going to talk about the deformation rigidity of Fano manifolds. Let me just briefly recall what's a deformation of variety. So in my talk, deformation is a flat surjective. A deformation is just a flat surjective map. Flat surjective map from some variety capital X to some base B. With the central fiber is just the given variety X. And usually we assume the base is smooth and connected. And usually in my talk, I will only consider smooth deformation, which means every fiber is smooth. So this is just a picture from this Hatshon book, and also a deformation of Guangzhou Tower, and also some deformation in your daily life. So just this is a picture that I took several years ago. And also we can create your favorite deformation. This is my daughter, and when we move down, then we take many pictures, then you get a deformation of her. And then what do I mean by rigidity? Rigidity means this variety, when you deform, when you deform, then it remains the same. Mathematically, which means, I have a technical assumption that the fibers are projective. So whenever you have a smooth deformation with smooth fiber, with projected fibers, and then every fiber should be isomorphic to the given variety X. So this is quite a strong restriction on the variety itself. You can construct many varieties which are not rigid. So the main problem is to try to find the varieties which are rigid.
Can you relax projectivity of fibers to properness of the morphism?
Many of that depends. In my talk, one part is of bigger number one, then I think it's okay. The other is of high bigger number. I'm not sure. In fact, this is the most strong. You can also replace by K fibers, for example, and then I will come back to this. Then it becomes more complicated, more difficult, this problem. So when we restrict to projective fiber, then we can do something. We can do something. So I will come back to this question afterward. So by this well-known Harris-Smith's theorem, so we know whenever you have this smooth deformation of projective fiber or complex manifold, then there are different morphisms. So in particular, the topology will not change. In particular, this would imply P1 is rigid. But any smooth projective curve or genus of higher genus is not rigid. You have the modular space of curves. And then you have also PN is rigid. PN is rigid. This requires a little bit more work. For example, this follows from the work of Hertzberg and Kodeha, and then by Yao, which says when you have a compact Kähler manifold, if it's homomorphic to PN, then this manifold is itself is isomorphic to PN. And for this proof, this proof goes as follows. So first of all, we show this X is homomorphic to PN. So you can deduce the Birch numbers. Birch numbers are just the same as PN, and then from this you can deduce the Horty numbers. As we assume it's a Kähler. And then from this you deduce the Horty number are the same as the project space, and in particular you get the peak group is generated by just one generator. And then you look at the pullback of this generator. And then there are two cases. Either this pullback is just the L itself, which means the L is ample. And then this would imply X itself is just Pn. But then the difficult part is when the pullback of the ample number on Pn is minus L, is negative, and then we need to use Yale's theorem to show in this case X is a Bohr quotient, and in particular it's not simply connected because it's a Bohr quotient, so the fundamental group is quite big. So this exclude this case. So in particular, this would imply X is just isomorphic to Pn. And then naturally, you may ask, for example, what happens for other varieties, for example, hyperquadrics, Q2n. Even dimensional hyperquadrics, this has been done. But for odd dimensional hyperquadrics, I don't know if this is true or not. And also, in this theorem, we assume that this is a compact Kähler. So this Kählerness is quite important. In particular, this would imply this is related to the existence of complex structure on the 6-dimensional sphere. So assume this 6-dimensional sphere has a complex structure. And then we can choose just one point, and when we block this point, and then this X is just block one point. So this is diffeomorphic to this 6-dimensional sphere with the connected sum of this P3 bar. Means you change the complex structure, and then you shrink this S6 to one point, you get the diffeomorphism to this P3 bar, which is diffeomorphic to P3 itself. So this would give you a variety which is diffeomorphic to P3. But then you compute this C1 of this blow up of one point. Then you find that this is different to this C1. I think this is 3. The intersection of this C1Q. This means that this X is not isomorphic to this P3. So in particular, this would. Yeah.
Sorry. So you're explaining that because of this proof, it's not homeomorphic to P3, but it's diffeomorphic to P3, but it's not isomorphic to P3. But is it related? Can it be a deformation of P3? I think
you
a question about deformations. So does it fit into some deformation family?
Kern classes
you mean
are stable
P3?
deformation. Of course not.
Yeah,
So X cannot be obtained as a deformation of P3.
Kostya, Sasha answered your question. Chern classes are stable.
Chern classes are stable on deformation. Okay.
Okay. So this comes back to Sasha's question before. So if we drop the projectivity condition, then this becomes much harder in this theorem. And then, for example, Xu in the 80s, he proved the rigidity of this Pn under Kähler deformation. And Huang extended this to deformation rigidity of Qn hyperquadrics. But no other results are in this setup. So this is why I will only restrict it to projective deformations. Average fiber is projective.
But I'm sorry, isn't it enough to assume that the central fiber is projective?
Yeah. It's more or less the same. It's the same. In fact, we will split in 2 steps. one is local rigidity, and the other is to the central fiber.
Okay.
So what we really in the central fiber is projective.
Okay, thank you.
So we know this PN. So the next question is what are the next varieties to check this property? And so the first observation is if X is rigid, then it's locally rigid. Locally rigid means the nearby fibers are isomorphic to X. But this is this is a condition which is much easier to check, which can be checked by taking the first cohomology of the tangent bundle. So if you can show the vanishing of the first cohomology of the tangent bundle, then X is locally rigid. And then if X is Fano, then we have also the inverse. X is locally rigid if and only if the first cohomology of tangent bundle is 0. And in this case, this can be computed in many cases. For example, for rational homogeneous spaces, GMO-P. This has been done by Bott in the 50s. And then Bien and Pyong, they proved they computed this for Fano regular G variety, including, for example, for toric variety. And then Basquiat, Behan, they studied some 2-orbit varieties, Horror spherical variety. And then myself with Bai Chenyu and Manuel, we have a classification of complete intersections which are Fano or in GMO-P, which are locally rigid. So next step is, for example, try to show the rigidity of GMO-P or other these varieties. But even for this simple product, for example, P1 cross P1, P1 itself is rigid, but then if you take the product, it's not rigid anymore. You find that this can be easily constructed, well-known construction, embedded this hypersurface in P1 plus P2, and then the central fiber becomes some Hertzsprung surface of degree 2A, and this is for any A. So you have many different deformations. So this shows the X0. This shows P1 plus P1 is not rigid in our sense. And one particular example is if you take a P1 plus Q1. Q1 means conic in P2, embedded in P2, and then embedded in P5. And then this has several deformations, and only deformation in this P5 is it can be deformed to this P01 plus O3. So this is only possibility in P5. Even later on, this will appear in a rational homogeneous space, the VMRT, and then they need to use this to exclude some cases. And then we come to this GMO-P, so we need to introduce this simple lineage of the ADE type. This is simply laced, and also BCFP. This is non-simply laced, and also this is a picture from subway in Hong Kong. So you can see also this ADE on the right, on the left, and also BCFP on the right. So in our daily life, it's also distinguished. And in fact, the geometry is quite different between simply laced and also non-simply laced. And there were a particular example of GMO-P is called irreducible Hermitian symmetric spaces. So this is given by some GMO-P with a maximal parabolic P. And the condition symmetric means this P acts on the tangent space or the irreducible repetition. And of course, these varieties are classified by any Gartin, which is given by these varieties. For example, type A, you get a Grossman, and type 3, you get an Gaussian Grossman.
That's the
Yes.
same as cominuscule, right?
Huh?
That's the same as the cominuscule condition, right?
Cominuscule it's yeah. I think it's there is one difference with cominuscule. I don't remember. There is one variety which is not a cominuscule.
Really?
So IHS in this talk is just this variety.
Mhm.
Cominuscule is hyperquadratic, maybe even dimensional hyperquadratic or odd dimensional is not cominuscule.
Okay, but
There is one small difference between cominuscule.
okay.
And this is spin variety. This is spin variety and also Cayley plane, so E6 mod P1 or P6, and also E7 mod P7. And then in the first part, we will always assume a chemo P is a bigger number 1, which means P is the maximum. And then in the marked thinking diagram means we just mark one node. And one particular example of type Bn, and this is a particular example, B3 mod P2. B3 mod P2 is just this corresponds to this marked thinking diagram. And then if you look through this means this parameter lines on this Q5 on this 5-dimensional hyperquadratic. And then you can compute this dimension is 7, so you get a 7-dimensional variety, and then this will appear later on as an exception because the variability. So I will talk about this. It comes here. So this is a theorem of Huang and Bock about series papers. So chemo P is of big number 1 is rigid in our sense, if and only if chemo P is not of this type, of this B3 mod P2. B3 mod P2 is not rigid. In fact, why it's not rigid? In fact, Basquiat and Behan, in fact, they constructed an explicit deformation of this B3 mod P2. In fact, they can embed in this in some project space V1 and V2. V1, V2 are reducible reputations of this G2, with one the omega 1 and omega 2, and then you can consider a kind of orbit of this line. T is the parameter, and then when T is non-zero, this orbit closure is just the B3 mod P2. And then when T is 0, then you find that this central fiber is not homogeneous anymore. So this gives you an explicit deformation of this B3 mod P2. And then recently Huang and Li, Qifeng Li, they showed this is the only possibility to deform this B3 mod P2 to another variety. And also in this approach, this bigger number 1 is important. As we have seen, this P1 cross P1 is rational homogeneous, but it's not a bigger number 1. So you can deform to many other varieties. So it's not rigid. So this is why you call B1 equals to 1 in this approach. So what's the main?
Just confirm. So this is an example when, as you're right, the variety which is isomorphic to the Grassmannian is degenerates, specializes to a variety which is not isomorphic to the Grassmannian.
Yeah. Yes.
Even not homogeneous. And if we asked about, so can it be another way around? If your central fiber is the Grassmannian,
Okay.
sufficiently near
But the
fiber.
TMOP are definitely TMOP are locally rigid, so you cannot take the central fiber is TMOP, so nearby fiber is also TMOP.
Mhm.
Okay. So what's the key ingredients for the proof? In fact, they use the VMRT theory of Huang and Walk. What's the VMRT? So assume X is covered by rotational curve, and then you connect. You take a family of minimal rotational curve. Minimal rotational curve means you can sort. You can think of, for example, it's a minimum degree passing through a general point. And then so this is I fixed one point. This is one point, and then I consider all these minimal rotation curves passing through this point. And then for each curve, then you can take the tangent direction of this curve. If this curve is smooth at this point, and then this gives you one point in the projectivized tangent space. And then you connect all this tangent direction, then you get a subvariety on the projectivized tangent space. And then this is the VMRT. This is CX. And for TMOP of beacon number one, the VMRT is very easy to compute because the minimal embedding of this TMOP to project space makes the TMOP to be covered by lines. And then the minimal curve are just lines. Then you consider what's the set of lines passing through one point. For example, for Grassmannian, for this usual Grassmannian, so you mark one point. And then how to find the VMRT is you just drop out this marked point. And then you mark next a nearby node. And then this give you two thinking diagram. And the first one is just the project space. The other one is also another project space. So this give you the VMRT just the product of two project space. And then let's look at the exceptional case, B3 mod P2. B3 mod P2. Change the count. B3 mod P2, for example, for this case, this VMRT you drop out this load, and then you have two load, and then this is one is short, the other is known. So if you particular this give you the VMRT is P1 plus Q1. P1 plus Q1 in fact this is not rigid, as we have seen before. It can deform to some horizontal surface. And this gives you all the method to find the VMRT for TMOP when P is associated to long root. But if P is associated to a short root, then this does not work. Because in this case, TMOP is not homogeneous; it's just quasi-homogeneous. And in this case, it's more complicated to describe it. And then what's the idea of Huang and Mock's proof of the rigidity of TMOP? It consists of two steps. The first one is to show the invariance of VMRT, which means when you have a deformation of these varieties, the central fiber, the general fiber is TMOP. The general fiber is TMOP. So the general fiber is TMOP, and then central fiber could be some other smooth Fano variety, and then the minimalization curves on general fiber were deformed to a minimal rotation curve on the central fiber, and then you consider the deformation of this VMRT, and the first step is to show the central fiber has the same VMRT as the general fiber, and then we can use the reconciliation of TMOP from each VMRT, which says whenever you have smooth projected variety of beacon number one, which has the same variety of the GMO P, then the variety itself is isomorphic to GMO P. So this is done. But the recognition theorem is quite a hard problem, which has been treated by several people. And the exception, let's come to this exception of B3 model P2. This VMRT is P1 plus Q1, and in this case, it can deform to this variety. So the first step failed. So this is why it becomes an exception. And so let's come to the higher big number case. In this case, we cannot expect it to have rigidity. For example, even for P1 plus P1, it's not doing. So this is why we put some more stronger condition on this deformation, which means Fano deformation, which means the central fiber is also Fano. And then P1 plus P1, then it can be deformed to Hertzsprung surface. But if you assume the Hertzsprung surface is Fano, then you have no choice. It's just P1 plus P1. So in particular, P1 plus P1 is rigid under Fano deformation. So in this setup, we have higher big number, then it's better to assume the central fiber is also Fano. And in particular, this can be firstly proved by Weber and Wisniewski, who showed GMO B is rigid under Fano deformation. And then Chifoni showed if a product is rigid under Fano deformation, then each fiber is also rigid under Fano deformation. So this can reduce the product case to just a simple case. And also Chifoni showed many varieties of GMO P which are rigid under Fano deformation. But still, we have one example of this is a homogeneous variety which is not rigid under Fano deformation, because this can be deformed to this project space, this projective variety which is Fano. So even for GMO P, it's not completely classified, which are rigid. And then our first result is about a wonderful complication. What's wonderful complication? This is the Fano variety which compactified G, any given semi-simple adjoint knee group, in a nice way. So in fact, this has been constructed by De Contini and Porchese. So they show that there exists a unique Fano smooth G cross G variety X, just the G bar, which satisfies the following properties, which are very interesting properties. First of all, of course, it has an open orbit, it's just a G cell. And the boundary dividers are very nice. They are all smooth dividers with normal closure. And the number of dividers are just the rank of the knee group. And then the third one is about the orbits. So the orbits are just given by the intersections of these dividers. So each orbit is given by the open part in the intersection of some dividers, some boundary dividers. And for example, for PSL2, and then the wonderful complication is just P3. The complication is just given by you just embed PSL2 into this P of endomorphism C2. It's just P3. So the boundary is just P1 cross P1. Just you have just one boundary divider. So, and also if the group itself is product, then the wonderful complication is just the product of each factor. And also the beta group is well known, just given by the boundary dividers. And how to construct this wonderful complication? So this we use some representation theory. So you take any regular dominant weight, and then you find the irreducible representation of this corresponding to this weight. And then you just embed this G into the PGL of this V lambda. And this is embedding because we assume the G is a joint type. So there's a low center. And so you get an embedding into this one, and then you take the closure of this embedding into this particular space. And then you show this is smooth and satisfies the given property. And in the case of type A, you find this wonderful communication is it can be constructed by explicit blow-ups. You find in type A, so the group is just the PSLN, and then you embed this to the endomorphism group, endomorphism particulation of the endomorphism of vector space of this V, and inside of this, so you can think of this as matrices, and then this is rank 4 rank matrices, and then no rank matrices, and the rank 1 matrices are just given by this product will produce spaces. And then what you do is you block first the lowest strata Z1, and then Z2, strict transform Z2, and so on. Then in the last one you block the strict transform of this ZL-1. No, ZL-2, because ZL-1 becomes a hypercircuit. Okay. This is L plus 1. So this is a hypercircuit. So you block till the strict transform of ZL-1. And then this becomes a smooth Fano variety, which satisfies the given property. And this is an explicit construction of this wonderful communication. So our main theorem is that this wonderful communication of G is rigid under Fano deformation. So the proof is quite technical, and we first of all we can reduce to the case when G is simple by Shifuni's result, which says that whenever you have a product, then if the product is rigid, if and only if each factor is rigid, so we can reduce it to the case of just the G is simple. And also in this case, Bian and Kuhn they show that these regular G varieties are locally rigid. So this wonderful communication is one example. This is locally rigid. And so whenever you have something locally rigid to show the rigidity, we only need to reduce to this particular situation where you have a small deformation of this X. You have a small family over this disk delta, such that every fiber except one, except 0, is isomorphic to our wonderful communication of this G, and then the central fiber is Fano, and then what you need to show is that the central fiber itself is isomorphic to this wonderful communication of this group G. So this is the main setting we need to prove, and I will give the proof later on, and so for this theorem, so there are still some questions which remain. For example, we assume the every fiber is Fano, and can we remove this Fano condition, or even can we remove this projectivity condition? This is still we don't know. So for example, can we? Yeah, this is the most strong question. Can we show if it's rigid under Kähler deformation? And then the second question is about the rigidity of wonderful symmetrical variety. This G bar, this is just one example of this wonderful symmetrical variety. And these varieties are also locally rigid by Bien and Bouillon. And recently, last year, Bien, Bouillon and Kim and Behan, they have studied the VMRT of this wonderful symmetrical variety. And so, yeah, I studied their VMRT. Yeah, our approach does not apply to other symmetrical varieties. And also, you may also try to study the rigidity of GMO hypernet sections or linear sections of GMO-P. And the local rigid case has been classified by myself with Manuel and by. So this is a first result, and then second result is a recent work with Yifei Chen and Qifeng Li. We studied picker number 1 case. So the wonderful complication of G is a higher picker number. And then this is picker number 1 case. Picker 1 case, but we restricted to some very special varieties. These are 4 special which are rational homogeneous. The first one is Lactantian 3,6, and then this is Grassmannian 3,6, and S6. S6 is a spinal variety corresponding to D6. D6 means this is SO12, and also E7 mod P7. And then for these varieties, we take a hyperplane section of this one, and then we show these are rigid under Kähler deformation. In fact, these are picker number 1. So Kähler deformation is the same as projective deformation. So there's no difference. So your first question, you may wonder why we are interested in this variety. These 4 varieties looks very special, and why we just consider this hyperplane section of these 4 varieties. In fact, these 4 varieties is quite amazing. It has many interesting properties. In fact, it comes from this geometric frequental magic square. In fact, it has 4 lines. Each line has 4 varieties. So first line is F4 mod P1 and E6 mod P2, E7 mod P1, E8 mod P8. And then if you take the first line and then you take the VMRT, for example, VMRT of this one is just given by Lactantian 3,6. Maybe I can draw this. This is not so like this. Like this. This is F4 mod P1. F4 mod P1, and then you mark this point, and then the VMRT. This is a long root, and then the VMRT is you need to cut out this point, and then mark this point. And this point is just given by this, which is the Lactantian 3,6. It's equivalent to this variety. And similarly for this E6 mod P2, and then you get Grassmannian 3,6. Because E6, 1, 2, 3, 4, 5. Mod P2. P2 means you mark this point. And then you need to remove VMRT, you remove this point, and then you mark this point. So this is just a Grassmannian 3,6. So you get this one, and so on. So the other is same. And then you take again VMRT of this second line. VMRT second line, then this give you so you need to remove this point. You mark this point. But then you have this double line, so you get the second Baohua embedding of P2, and then this is just the P2 plus P2, and this is Grassmannian 2,6. This is the OP2, and then you take a hyperplane section, you get this. What's the most interesting part is you take a hyperplane section of this third line, then you get a still rational homogeneous variety. And all these four varieties are this upstairs. The four varieties are just the second line in this magic square. So this is one motivation for this variety. And also these varieties are just one example of this variety. This because in our classification for locally rigid varieties, these appeared in our list. And also the second reason why we study these four varieties because in Fano he classified the smooth projective symmetrical varieties of peak number 1. There are two types. One is G2 type. In this G2 type, we have two examples. And then A2 type. A2 type is given exactly these four varieties, which we studied. So in fact, we start our theorem can be rephrased. And for these four varieties, these are rigid. But for these two examples, these G2 cases, there's one case we can show is rigid, but the other one it's still quite difficult to show the rigidity.
I'm sorry, what does symmetric mean here?
Symmetrical, yeah, symmetrical means means on the open part. Yeah, maybe later on I have some. Okay. So I didn't write here. Means this for example, this hyperplane section of this one, it has an open part, which is which has an open part, which is G mod H. Then H is symmetric. H is contained in the stabilizer. Is one component of the. You have some evolution on this G. On this G, the stabilizer, the fixed part of this this evolution, it can have several components. So this H is sitting between this and also the connected component. So this is usual definition of symmetrical spaces. And then this symmetrical variety, particular symmetrical variety is a projective completion of this symmetrical spaces. So why is there only these four examples? Because he added this condition of peak number 1. And in other cases, for example, this wonderful symmetrical variety studied by Hyun, Kim, and Behan. So this is it could be of higher peak number. So for peak number 1 case, there are only these four cases. Okay. Also, another question which remains is for example, from this theorem, for example, this S5, this is the 10-dimensional spinor variety, and you take just hyperplane section of this 10-dimensional spinor variety. This is Mukai variety, and then this is rigid. This is just follow from Mukai's classification of Mukai variety. And then our theorem says this is the second spinor variety, S6, hyperplane section with S6 is also rigid. And then by my work with manifold, we show S7 hyperplane section with S7 is also is locally rigid. But then the problem is, yeah, for the moment I don't know how to show if this S7 hyperplane section with S7 is rigid. And you find that if you take Sn, if n is at least 8, then it's not locally rigid. So this cannot be rigid. So the only case which remains is S7 intersect with hyperplane section with S7. I don't know if this is rigid. So this is 20 of dimension 20. And why this can be treated because this VMRT is quite simple. VMRT is just order symmetric Grassmann. This Grassmann 27 with order symmetric form, and this is quasi homogeneous, but this is rigid by Huang and Li. So in particular, we can show the VMRT is rigid. So in particular, the first step of the Huang and Mox approach works, but then the second step is quite difficult because we don't know how to recognize this hyperintersection from its VMRT. And also similar question for this hyperintersection of Grassmann. Without Grassmann 3.6, this hyperintersection is rigid, but then Grassmann 3.7 or 3.8, this is not known. I suspect maybe the two are not rigid. And so in the remaining time, maybe I come back to the proof of the first result on this rigidity of the wonderful communications of a joint knee group. So the proof is quite similar to the case of Huang and Mock for the first step. But for the second step, this is much harder. We do not have the recognition theorem. So let me first of all recall the mean motion curves on this wonderful communication. In fact, this G bar, this has a higher peak number. The peak number is the same as the rank of G, so it's a high peak number. So it's quite surprising that we showed there exists a unique family of mean motion curves on this G bar. This is somehow unexpected. And also the VMRT is quite simple. The VMRT is just given by the unique closed G variety GG orbit in this adjoint representation of this G of this G. So this is just the pure meme. So this is Fano contact variety. If G is not of type A, but if G is type A, is the Fano contact, this variety is projected by the tiny bundle, coordinate bundle, which is just a linear hyperintersection of this product. But type A, we show that the VMRT is the product of two projected spaces. And this is just a picture why this is true. Because for type A case, we have seen before. This is given by the wonderful communication is given by successive blow-ups. So you start with blowing up the first stratum. The first stratum is just the project space, the product of two project spaces. And then you successfully blow up the bigger strata. And then this is why each VMRT is just this one, because you blow up this blue line, blue part, and then you get this transformation of this line. This line will give you the mean motion curve on the block. And so we need to study this VMRT. The VMRT is just given by homogeneous Fano contact manifold, which are given by this variety. You can forget this. And then you can say there's one particular example of this. For example, this is this BL model P2, this appears as a VMRT. Also, we have seen this B3 model P2 will become an exception, which is not rigid on the final deformation. So in particular, this is theorem. So this final contact manifold is rigid except this type B3. So type B3 is the most difficult part to our proof. So the first step is to show the invariance of VMRT. As we have seen, this B3 is not rigid on the deformation. So in fact, for this B3, we need to do much work. And so the first is again we show the invariance. To show the invariance, so we just take the setting, the usual setting. You have every fiber outside 0 is isomorphic to this wonderful communication, and then the central fiber is also Fano by assumption, and then you take a local section of this deformation, and then you get the deformation of this Wehrmann-T. And then by Huang's theorem or by Huang-Mock's theorem, so you know this Fano product varieties are rigid. They're under this deformation. So you see the central fiber is also isomorphic to this Fano contact, except this B3 case. And then we need to not only show abstractly these varieties are the same, and also we show the embedding are the same. And then we need to do a little bit more work to show this invariance in type A, because type A is Pn cross Pn. It's not rigid in general. It's rigid only under final deformation, but in our case, this is deformation of Wehrmann-T. We cannot assume the central fiber has a final Wehrmann-T. So we need to really rely on the explicit construction of this block, and to show the central fiber is also PL cross PL. And also the invariance of type B3 is really complicated. In fact, we not only consider Wehrmann-T, but we consider again Wehrmann-T of Wehrmann-T. Because this Wehrmann-T give you this B3 mod P2, and when you take the Wehrmann-T of B3 mod P2, and then you get the P1 plus Q1. P1 plus Q1, then this has two possibilities. It can deform either to itself or deform to another physical surface. And then we really do a little bit a lot of work to exclude this case, to show that this cannot happen. This is not possible. And then we use the recognition by Wehrmann-T to show this central fiber is also B3 mod P2, which means the deformation given by Behan and Batsky cannot happen in this situation. And then there's the first, so we'll get the first step to show the Wehrmann-T are the same. But then the second step, recongratization fails in general, because we have a lot of examples. For example, if you take the Lacrangian Grassmann, or even for this simple example, then it has the same Wehrmann-T, but when you take different Hepburn sections, you get non-isomorphic variety, so you cannot recognize by each Wehrmann-T. And also one particular example is 10-dimensional spinor variety. You have in fact two types of codimension 2 sections. One is which are not isomorphic, but with the same Wehrmann-T. But the special one is not rigid, locally rigid. The other one is locally rigid but not rigid. And then if you have high big number, then you get many more examples. So what's the key point or key difference between this approach and the Huang and Mock's approach? In fact, the new idea is we cannot recognize the central fiber by each Wehrmann-T, but we can compute compute the first cohomology of the tangent bond and try to show the central fiber itself, X0 itself is locally rigid. If you show the central fiber is locally rigid, then it's isomorphic to the nearby fiber. But so it's isomorphic to this wonderful communication. So this is done. So the main point is can we show this the vanishing of this one? To show the vanishing of this one, so we use the central fiber itself is Fano. It's Fano, so you have many vanishings of higher cohomology. And then what's remaining is just H1, H0, and H1. So H0 minus H1 give you the overlap characteristic of the tangent bond, which is the same as the nearby fibers. And then so in this case, we get the dimension of this one is given by the automorphism group, dimension of the automorphism group of central fiber minus this constant. And so in order to bound this H1, we want to show H1 is 0. So we just need to bound, give an upper bound for this automorphism groups of the central fiber. So we need to bound this automorphism, and this can be done by using VMRT. In fact, we have an inequality and upper bound for this automorphism group, given by a dimension is given by this dimension X plus this dimension of the automorphism group of this VMRT, and also prolongations of VMRT. All these are dimensions. And also equality holds if and only if X is equivalent complication of Cn. And also we have classification when the last term will vanish. I just jump this application. And then to bound this central fiber, in fact, we just plug in this inequality here, or inequality here, and then we get this H0, this automorphic group of central fiber has a dimension with the upper bound of dimension G plus this automorphic group of VMRT if it's not of type C. And then it helps out this automorphic group of VMRT just one dimension G, one higher than the dimension of G. And so in particular, this implies H1 is at most 1. And so there are two cases, either H1 is 0, so then we are done, because in this case it's locally rigid, or H1 is just one-dimensional. In this case, we have equality upstairs, so this becomes the equality, and then this implies the central fiber itself is an equivalent complication with Cn. So this gives you a very strong restriction on the central fiber. And then our next task is to show this cannot be an equivalent communication of Cn for the central fiber. Maybe I need to be quick. Maybe I just say a few words. So in fact, we need to divide to several cases. For example, this cases, if G is not of these types, G2, F4, and E8, because these three cases correspond to this root lattice is equal to weight lattice. And then if it's not the case, then we are done. Because if it's an equivalent communication, we have this should be an equality. So if it's not an equality, then we are done. So for these cases, it's either. And then for this three cases, this is a little bit harder. And then we need a more detailed analysis by using by taking a two-dimensional torus, by considering the fixed points of this action, and to get to cut down to surface case of photic surface degenerate to an equivalent communication of C2, and then we really study this toric variety, the toric surface in much detail, and to show this is not possible. And then the only case which is remaining is type CL case, type C case. For type C case, we also give a construction of the type C wonderful communication with type C by successful follow-ups, which is quite similar to type A case. But then this follow-ups is not a follow-up along follow-up from smooth subroutine, but a follow-up from some singular spaces. So this is like content graph mania, you model out by some evolution. So this is singular variety, and then you successfully follow up this one. And finally, you get a smoother variety, which give you the wonderful communication. And similarly for this type B or type D, we have also a similar construction for these graphs. And then for type C, how do we show the rigidity of type C? In fact, type C, in fact, we show in fact type C is a spherical variety. And then then we show this spherical variety has the same kind of fan, we show the central fiber is spherical variety with the same kind of fan as the wonderful communication, and then we use spherical variety theory to reduce the isomorphism between this central fiber and also the wonderful communication of type C. So I think my time is up, and that's all I want to talk. Okay, thank you.
Thank you very much. Are there any questions to Baohua?
Maybe I have general question. Your definition maybe can be generalized as follows. Suppose you have deformation only a finite number of deformation types.
On the
Finite number of deformation types of some, say, Fano variety. What can I say? Do you know examples like this? Not just one deformation,
but I think we
yeah.
this example on the slides. It's
yes. B-stream with P, B-stream with P2. This give you one example. It has two deformation types. They show these two are only possibility.
How about Picard number one?
This is one become one case. This one.
Yes. So it has two deformation types, right?
Yes, only two. Yeah. This is one, and they show the central fiber either isomorphic to B-stream or P2 or isomorphic to this X0.
I think you also mentioned the section of S5, right?
Oh yes, S5 also, yeah. S5, if you take a codomain 2 linear section of S5, I think Sasha knows also this. Don't know where is it. Yeah, 10-dimensional spinal variety, you take the codomain 2 linear section. It has two types. Either isomorphic to this general one, or the special one is I don't remember where I put it.
By the way, what happens with VMRT in this example?
10-dimensional spinal variety, or they have the same VMRT. Okay, I remember that. or is on the recognition.
I mean, for this codimension 2 linear sections.
Yeah, this one. This one.
They have the same.
Yeah, because in this case, the VMRT is Grassmannian 2.5.
That's for S5.
Is Grassmannian 2.5 for S5. S5 Grassmannian 2.5. So you take a codimension 2 linear section, so they are all isomorphic.
Okay.
So this is why the relation doesn't work. And also, I think it's quite interesting. It's quite interesting for this S7 case. So S5, S6 we know, and for this example, this S7 hypersection of S7. I don't know. I don't know how to treat this case.
But what is the stabilizer subgroup of a hyperplane section in this case?
I don't understand. What
is the stabilizer of a hyperplane section in the S7 example?
So
I guess it's some group of dimension 28, right?
Yeah, 20. S7 is 21. So I don't remember. I think we computed this in. Maybe it's not quite homogeneous. I don't. I did this in our paper with Manuel. I don't remember exactly.
I can check the paper. That's not a problem.
Yeah. Okay. It's quite homogeneous. So the stabilizer is SL3. Even it has the action of this G2 cross G2. So even this is a quasi homogeneous variety. The open part is G2 cross G2, modeled by SM.
Okay. So 28 is
it's quite
14. Okay, interesting. I see.
Yeah.
Thank you.
So this example is quite related to this to this example, this G2. Because in this G2, it has two examples. One example is quite easy to treat, but the other G2 is a little bit hard to do.
Okay.
Okay.
Other questions? Maybe I have a couple of very short questions. So you at some point you took this magic square, took the second line, and studied hyperplane sections. What would happen if I took the first line instead of the second one and ask the same question?
You will take the hyperplane section of this one?
Yeah.
But then this is not rigid, not locally rigid.
Not locally. So the hyperplane sections are different themselves, right?
Yeah. It's not locally rigid, so you cannot talk about rigidity.
Also, another question: and what do we know about rigidity in Fano threefolds? I mean, not Fano rigidity, but just rigidity.
Just in the P one case, I suspect only P3 and Q3.
You expect that only P3 and
I never thought in this way.
Actually, but in most cases there are moduli, so there is no question like this. But for instance, there's one more case when there is no moduli, V5.
You mean V5?
Quintic, like quintic Delpez threefold. It has index 2 and the generator of Picard group. Actually, it's just a dimension 3 linear section of G25.
Yeah, G25. Okay. For this one,
So it pretty much falls into the same type of varieties we are studying.
Yeah. Oh, yeah. This is a good question.
This
Yeah,
one
I
is
never
not
saw.
rigid. It's not hard to check. It's easy to check that it is rigid.
It's easy to check that
It is
that
rigid.
what?
I mean, at least as Fano variety, it's definitely rigid.
No, as Fano variety, you can just
Yeah.
the invariance, the numerical invariance should be preserved. So it's
I'm sure it's also rigid without this.
Yes. Now I understand. Yeah, it should be rigid. Yeah, because you have this so the Grassmannian 2.5, so it's a delpedal variety. So we deform, I think the index will not change. So when you deform, you still get a delpedal.
yeah, but if you don't assume that the deformation is Fano,
It's Picard number 1. That's automatic.
It's become number 1. Yeah, it's become number 1. So if you assume it's Kellen, if you do not assume it's Kellen, I think even for Grassmannian 2.5, we don't know how to prove this.
Mm-hmm.
Yeah, the Kellen, if you assume it's Kellen, then it's okay.
Mm-hmm. I see. So other questions?